So we've been doing some work with the rate version of the second law when looking at open systems. Now, inevitably, when you do these problems, you'll get to the point where you need to fix the states for the specific entropies. At that point, you need to ask yourself, what's the fluid? Because if you don't know the fluid, you can't find the specific entropies, and you can't figure out if the entropy generation rate is positive, 0, or negative. And then you won't be able to tell if the process is possible. So how do we find specific entropy? So if the fluid is water, then we have to figure out what's the phase. If it's a superheated vapor, it's not that hard. We look it up in the tables in the same way we would for specific internal energy or specific enthalpy. Same thing if it's a two-phase mixture. Again, we look this up on the tables trying to find quality. Now, if it's a subcooled liquid, things get a little bit more interesting. Maybe I'll be able to look this up on the tables and do some double interpolation. But remember, when we were trying to find the change in specific enthalpy, here we would say that delta H was Cp times delta T. We have a similar equation for subcooled liquids when we're trying to find the change in specific entropy. But now we have Cp times the natural log of T2 over T1. So it's not the temperature difference, it's the natural log of the ratio of the temperatures. And here we have to notice not to use relative temperatures, but to use absolute temperatures. So what do we do if the working fluid is air? Again, we'll have a choice between variable specific heat and constant specific heat. If it's variable specific heat, we'll use this equation. Now here, notice there's no Cp or Cv in this equation, and that's what makes it variable specific heat. Here we have some portion of the change in specific entropy that's due to the change in the temperature. But then another portion of this change is also due to the change in pressure, and that we can model analytically. So there's two parts. This S superscript 0 term, which I look up on table A22 for air, or A23 for other gases. And then this pressure term, which I have to calculate analytically. Now, I can also assume that there's constant specific heat. And if I do that, I still get, if I know the change in pressures, I still get this same second term. But now my change in entropy that's due to temperature, I get an analytical term for this that's related to Cp. And if I know the change in temperatures and the change in specific volumes, then I'll use this option where my temperature term is related to Cv. As always, the variable specific heat analysis will be more accurate than the constant specific heat analysis, but VSH usually takes longer than CSH because we need to fix states on a table, or we need to maybe do some linear interpolation. So let's try this out in an example. So here we're given a heat exchanger. We're told something about the mass flow rates of air and the refrigerant, and we're given some information at the different state points at the inlets and the outlets. We're told that the heat transferred from the air to the refrigerant is negative 9.5 kilowatts and asked if this process is possible. So we've talked about how for heat exchangers we have some choice in what our control volume will be. And in this shorts video, I'm only going to look at the entire control volume. If you want to see how to do it when you're looking at the control volume of only the air or only the refrigerant, check out the long version of this video. If I'm doing a second law analysis on the whole system, I can assume that the system is at steady state, that it's adiabatic, so all the heat lost from one side of my control volume goes to the other. But it's not one inlet and one outlet. So now I have an expression for this entropy generation rate. turns out I need to look at the inlets and the outlets of the air and the refrigerant to figure this out. But to do this, I have to find S1, 2, 3, and 4. So on the refrigerant side, it's not too bad. We'll just look stuff up in tables like we normally would. I have one case at state 3 where it's a two-phase mixture, and at state 4, it's a superheated vapor. I won't go through the interpolations here, but I got some values for specific entropies. Now the trickier part is, what do I do with the air? Here I have a choice to make. I can use variable specific heat, where I'm looking things up on table A22, because this is air, or I can use constant specific heat. And if I use constant specific heat, I got to figure out if I know the temperature ratios and the pressure ratios, or do I know the temperature ratios and the specific volume ratios. And in this case, I know about the temperatures and the pressures, so I'm really choosing between option A and option B on this slide. We'll do it both ways here. So if I want to find the change in the entropy of the air, I can look it up on the table. So I go to table A22 and I find S superscript 0 for my two temperatures. In this case, 305 and 295. So here, this is not the specific entropy. This is this S superscript 0. So now I put these terms into my equation, and because I know the pressure ratios, then I can get delta S of the air as it goes through the system. Once I know that, I can put all of that into my second law expression and get that the entropy generation rate term here is positive. So this process is possible. So I can do this with constant specific heat as well. Remember, I'm choosing equation B because I know the temperatures and the pressures. Here, I can evaluate the change in entropy of the gas, and I see that I get almost the same answer as the change in entropy for the gas when I used variable specific heat. And that's because my temperature range here is fairly small. Now, if I put this back into the equation for entropy generation, you'll see that I'll again find that the process is possible. So notice that this problem will get interesting and more difficult if I only look at the hot side or the cold side of the heat exchanger. If you'd like to see how to do that analysis, check out the long version of this lecture. Thanks for joining me again on Thermal Shorts. I'll see you next time.